Thanks, hi everyone, and thanks for coming to this talk so late in the afternoon. So as he said, my name is Johnathan Stauffer. I'm a PhD student at the National Solar Observatory and the University of Colorado at Boulder. And so in this presentation, I'm going to be talking about how ALMA can be used to study the presence of cold plasma within the solar atmosphere. And so having just said that, you might be thinking to yourselves, wait, ALMA can look at the sun? And the answer to that is actually yes. So ALMA has been used regularly to observe the sun since about cycle 4 in 2016. And its excellent sensitivity and its coverage in the UV plane makes it a really ideal instrument to study solar activity. And it's been used to study a wide variety of phenomena, such as atmospheric waves, sunspot oscillations, prominences, and a lot more. And so I realize that I'm kind of an outsider here, and that solar physics is pretty far removed from what most of you are doing day to day. So before I get into my research topic in particular, I'm going to start out with a little bit of an introduction about solar science with ALMA and why solar physicists are so excited about it as an instrument. Radiation in the millimeter and submillimeter range where ALMA observes can come from a few different physical processes in the solar atmosphere. But in most cases, for the sun, its formation is dominated by the interaction of free electrons with either ions or, to a lesser extent, neutral hydrogen. So it's Bremsstrahlung radiation. And because the radiation is being mediated by thermal particle interactions like this, the millimeter intensity is essentially directly tied to the kinetic temperature of the solar atmosphere via the Planck function. Furthermore, because the free opacity of Bremsstrahlung increases with wavelength, different ALMA receiver bands can be used to study different layers of the solar atmosphere. To demonstrate this behavior, I have a couple of pictures of the full sun taken at different wavelengths. So here on the left, you can see the sun as seen in the visible continuum, which shows essentially the visible surface called the photosphere. On the right, there's essentially a one-dimensional semi-empirical model of the solar atmosphere with the red arrow to mark essentially where we are. And so here in the visible, we're looking fairly deep down into the atmosphere. And what you see is mostly flat. It's dominated by a small-scale convection pattern called granulation. But you can see over here on the left hemisphere, there are some dark regions. Those are what are called active regions, essentially collections of sunspots with strong magnetic field. And the last thing I want you to see is essentially this limb darkening, right? So the edge of the sun looks darker than the center, and that tells us that the temperature in the solar atmosphere is decreasing with height in the photosphere. Now moving on to ALMA and millimeter wavelengths, we can see that the picture actually changes quite dramatically. So this is 240 gigahertz, so ALMA band 6, and we see that the sunspots are now surrounded by bright regions that we call plage, and that weaker bright spots essentially are peppering the whole solar surface, and that's what we call enhanced network. These are all manifestations of magnetic field. And lastly, we note that instead of limb darkening, we have limb brightening. So the limb is actually a little bit brighter than the disk center, which tells us that temperature is increasing with height. And if you do the radiative transfer from this 1D model, this all makes sense because the millimeter radiation originates further up in the solar atmosphere in a hot kind of extended region called the chromosphere. Moving on to ALMA band 3 at 100 gigahertz, it's more or less the same picture, but we still kind of retain that limb brightening, but now everything is a bit hotter, just like the model predicts. So now that we know what the sun looks like to ALMA, now I'm going to talk about why it's such an appealing instrument for solar physicists to study the chromosphere. The first and most important reason is how easy it is to interpret. As I described earlier, millimeter radiation is really closely tied to thermal processes in the solar atmosphere. And because it's essentially because of that, the millimeter emission is dependent almost entirely on local properties of the solar plasma. And so we say that it forms within local thermodynamic equilibrium, or LTE. And this is actually really rare for diagnostics of the solar chromosphere. For the most commonly used spectral lines that sample that same region, like H alpha or the infrared and visible lines of calcium-2, they become decoupled from the local properties of the atmosphere, essentially because particle collisions are rare enough in the chromosphere that the level populations of those atoms are set mostly by the radiation field, which can be coming from all over. So properly interpreting those spectral lines requires performing a lot of really complicated non-LTE radiative transfer calculations many times in order to fit a model atmosphere to your data in a process that's called spectral inversion. But with ALMA, you can just convert the intensity that you measure from intensity units like Joule per beam into Kelvin using the Planck function, and you're essentially done. The second reason is ALMA's excellent spatial resolution. So solar physicists have been studying the millimeter before they could start observing with ALMA, but they were really limited by the resolution of the telescopes that were available. So for example, you can look at these two images that are up on screen. So on the left is an image of H alpha, the H alpha line core taken from the Duns Solar Telescope. And you can see that there's spatial variation down to sub-arcsecond scales. Whereas on the right is that same image, but degraded to the spatial resolution of BIMA, the Berkeley, Illinois, Maryland Association Array, at 3.5 millimeters. And you can see all the fine detail is lost. All you can really tell is that there's something bright over here, and that's about it. And now you can compare that to the same image degraded to ALMA's resolution at 3 millimeters, and that's much, much better. So you still lose some of the very fine spatial structure, but you can still make out most of the details, including these long elongated fibrils, we call them, that are originating from this plage region. And lastly, the last thing that ALMA is really good for is its cadence. So as you can see from the movie that's playing on screen, the chromosphere evolves on very short time scales, usually minutes or less. And because the sun is so bright in the millimeter, ALMA is actually able to obtain snapshot images of the solar chromosphere every 1 to 2 seconds, which allows it to capture all of this variability. So now I could move on to my area of research. And so I'm interested in areas of particularly cool millimeter emission that are seen by ALMA that have been called chromospheric holes. These regions were first seen in band 3 emission by Masha Lukasheva in 2019, and then later in band 6 by João da Silva Santos. And his data are the ones that I'm plotting here on the right. And these regions are interesting in that they show brightness temperatures that are much lower than are predicted by most models of the solar chromospheric millimeter emission. So what are the actual properties of these chromospheric holes? So as I mentioned on the last slide, they're very cold, often as much as 3,000 Kelvin colder than the local average ALMA millimeter temperature. And they're also long-lived, as you can see in this movie to the right. So these band 6 observations span about 45 minutes on the sun. And they show a group of chromospheric holes on the left here that persist for the whole observing period. The movie also shows that these features are slightly spatially extended. They're often 5 to 10 arc seconds in size in band 6, and a bit larger when you look at them in band 3. And then lastly, I've found that these regions are almost always found adjacent to hot magnetic features, like this region of plage that you can see in yellow, kind of at the center of this field of view. So while we have observations of a couple of chromospheric holes within the ALMA archive, their origin in the solar atmosphere is still kind of a mystery. So the first, and in my opinion, most exciting possibility is that these chromospheric holes show the presence of persistent regions of cool plasma within the solar chromosphere. And this conclusion is supported by some simulations, like the one analyzed in the figure to the right. So here, when the authors included some more complicated physics, such as non-equilibrium hydrogen ionization, into this 2D simulation, they found that cool electron-dense loops of gas could be suspended by magnetic field up into the chromosphere, where they could, in principle, be detected by ALMA. However, it's not clear exactly how these loops relate to chromospheric holes, because this is a 2D simulation. And these simulations are very computationally expensive to run with non-equilibrium ionization and things. And so we don't really have any idea of how long these loops last and how they compare to the lifetimes of the chromospheric holes, or if these kinds of features would look the same or even exist in a more realistic 3D simulation that could be directly compared to observation. And then unfortunately, that's not the only possibility. Some 3D simulations, like the one analyzed to the right, show regions where essentially the formation height of the millimeter continuum, that is like the surface where it becomes optically thick, can abruptly shift from the chromosphere down to lower heights in the atmosphere, even into the solar temperature minimum, which is kind of in the upper photosphere. And so in this case, the chromospheric holes that we see wouldn't be cold gas in the chromosphere, but instead are literally holes in the chromosphere, where ALMA is instead seeing deeper into intrinsically cooler layers of the solar atmosphere. However, these 3D simulations, because they're 3D, are usually run with simplified chromospheric physics, and so we can't necessarily rely on them to really accurately reflect what the chromosphere is doing. So it's not clear if this kind of behavior is seen on the real sun, or if it's just a limitation of the kind of simulations we can do in 3D right now. And so there are two predictions, right, from the simulations. Either chromospheric holes are cold chromospheric gas, or they're just places where you're looking down and seeing cold photospheric gas. And so how can we distinguish between them? And for that, we need an independent measurement of cold gas in the solar atmosphere, which comes in the form of the infrared spectrum of carbon monoxide. So as you can see here, in most regions of the solar atmosphere, carbon monoxide is essentially limited to the temperature minimum, so upper photosphere. And so you can see that here. So black here is the temperature model, and then red is essentially showing you how sensitive the carbon monoxide spectrum is to changes in temperature at that height. However, if we try and model the atmosphere above one of these chromospheric holes, we find that the observations are consistent with pockets of cold gas in the chromosphere, kind of how, just like the 2D simulation earlier, and that those regions should have significant molecular formation. And so therefore, if chromospheric holes actually show the presence of chromospheric gas like this, then they should show enhanced CO absorption there compared to nearby regions. And so to test this, I designed an ALMA proposal executed last year in cycle 8 to essentially study chromospheric holes in band 6 and 7 while coordinating observations with the infrared spectrum of carbon monoxide. And so the main, so this just kind of goes over the how we set it up. Essentially, we tried to prioritize
3 more minutes.
Yeah, thank you. Prioritize wide fields of view in order to maximize our chances of capturing multiple chromospheric holes. And we also chose to propose for particularly long observing sequences because most of the observations we have are of static chromospheric holes. And we were hoping that by observing these regions for longer, we could get observations of one forming or decaying and therefore put some sort of bound on their lifetime and evolutionary timescales. So the rest of my slides are pretty much pretty pictures. So here is one of our band 6 targets, which is of a region of bipolar enhanced network. So there's a magnetic field over here, a magnetic field over here of opposite polarities. And then in the ALMA band 6, you can see these extended structure kind of connecting the two. And then as promised, here is a raster of the CO line core intensity that we tried to coordinate with. And we have about half of this mosaic is covered. So it's not, the alignment isn't quite as good as we would like, but you take what you can get. And then our second band 6 mosaic is of this sunspot here, which shows up about here in the mosaic, and then there's some plage kind of surrounding it. And then here is the CO in the same region. And this snapshot of the CO actually shows here and here these particularly dark regions, and those are transient absorption features in the molecular lines. And I'm really hoping that once I get the time resolved ALMA data split out to see if these regions correspond to the presence of chromospheric holes within the millimeter. And then lastly, we have observations in ALMA band 7 here of some unipolar enhanced network. And while we weren't able to get simultaneous CO data of this region, we hope to still look for chromospheric holes at this new wavelength and essentially compare their properties to the ones that are seen in band 6 and band 3 and any transient absorption features that we see in other CO observations of similar regions. And so in summary, I'm using ALMA to study chromospheric holes, which are long-lived cold regions that are seen in high-resolution ALMA observations of the millimeter continuum. Right now, it isn't clear whether these regions actually show cold gas in the chromosphere, or instead are places where ALMA is sampling cool photospheric plasma. And to distinguish between these possibilities, I plan to use simultaneous observations of ALMA with the carbon monoxide spectrum in order to search for evidence of excess molecular formation within these regions. And then additionally, I hope to use new band 7 observations to extend the search for chromospheric holes to lower layers of the solar atmosphere and characterize them. Right, and that's all the slides that I have. So